Hello, this is Team 4 in Stack 512, Spring 2023. Welcome to our final project presentation. COVID-19 is a global pandemic caused by the novel coronavirus, started in December 2019. COVID-19 has caused dramatic economic downhill in the society. In the beginning, the number of infection cases and death cases have been increasing on a daily basis. Center of Disease Control has started a mask mandate in July 2020 to slow down the spread of disease. The mask mandate has been in effect until April 2021. In December 2020, the medical companies and health officials have authorized the first 2 doses of COVID vaccine. Then, in August 2021, a booster shot is introduced as a complement to the series of vaccine. According to clinical studies, the 2-dose vaccine has an efficacy of 95% against infection. The efficacy of the booster shot is 96% against severe illness and death. Masks are able to block 80 to 90% of virus from the environment. Efficacy is measured in controlled experiments. However, in reality, the effectiveness of these measures is greatly impacted by many other factors. It has been a social study to investigate the effectiveness of vaccine, booster shot, and mask. Our project is a confirmatory study to associate these measures to the number of infection cases and death cases. Our project is based on weekly data of these parameters in Indiana.
Our data includes 6 continuous variables and 1 categorical variables. Data for continuous variables is up to date on CDC website and records the information in Indiana. Continuous variables includes total vaccine, dose 1, complete series, booster shots, infection cases, and death cases. Category is mask mandate, as the unit of infection and death cases is week. We transfer the unit of vaccine data from day to week so that our data can be used for further analysis and prediction. For research question 1 and 2, we delete the data containing 0 in infection and death cases, since it is nearly impossible to have 0 infection and death case in 1 week. For research question 3, since the booster shots are available on September 2nd, 2022, we delete data before September 2nd, 2022 in these research questions. Infection records the weekly infection cases in Indiana from December 31st, 2020 to March 29th, 2023. As vaccine takes 1 to 2 weeks to take effect, we postpone the infection cases 2 weeks to correspond to the effective vaccine. Death records the weekly death cases in Indiana from December 31st, 2020 to March 29th, 2023. Similar to infection variables, we postpone the death cases by 2 weeks to correspond to the effective vaccine. Total vaccine is the total number of administered vaccines per week in Indiana, which includes the first dose, second dose, and both first and second booster shots. It records all vaccines from different providers like Pfizer, Moderna, Novavax, and Johnson. However, the same people could receive multiple vaccine doses in different jurisdictions or from different providers. Thus, CDC's data may overestimate the total number of vaccines. The dose 1 and series are the total number of the first dose vaccine and second dose in Indiana per week from different providers. The same people could receive multiple vaccine doses in different jurisdictions or from different providers. The CDC's data may overestimate the total number of first dose vaccine but underestimate the total number of second dose vaccine. Booster records the total number of first booster dose vaccines in Indiana per week from different providers. Mask is the categorical variable which includes 0 and 1. If the mask is 0, it means the mask mandate policy ended in Indiana. If mask is 1, it means the mask mandate policy was still activated. The mask mandate policy required everyone over the age of 8 to wear masks both indoors and outside, wherever social distancing is not possible since July 27, 2020. The mask mandate policy ended on April 6, 2021.
Since question 1 and 2 share the same data and full model, we will be discussing them together. Question 1 investigates on whether complete series have significant impact on infected cases, given death cases, and first dose. Question 2 investigates on whether complete series and first dose have the same impact on infected cases, given death cases. The null hypotheses and reduced and full models are listed as shown. To start off, we need to perform diagnostic tests on the full model. These include Bruch-Pagan test for constant variance and Shapiro-Wilk test and QQ-plot for normality. As we can see from the result of the tests, before transformation, both assumptions are violated. Thus, we should perform transformations on x and y. We took the natural log of x and used Box-Cox transformation on y and obtained a lambda of 0.0303. After transformation, both violations are resolved. Next, we took a look at the added variable plots. Since the 3 plots all have slopes not equal to 0, the 3 predictors all have their marginal contribution to the model. After this, we examined the outliers and influential points in the data. Using studentized residuals, we discovered there are no y outliers. Using the hat matrix, we discovered that there are 3 x outliers, but they do not pose significant problems. According to df betas, df fits, and Cook's distance, there are no influential points in the data. Then we checked for the issue of multicollinearity in the model. According to the plot on the left, dose 1 and series seem to be somewhat correlated. From variance inflation factors we obtained, though none of them exceeds 10, two of them are close to 10, so we performed ridge regression. The K we chose for ridge regression is 0.14, which is where VIFs are first near 1. To deal with potential lurking non-normality, we performed bootstrapping on top of ridge regression. Then we obtained a bootstrapping confidence interval. From the confidence interval, we can see that the linear impact of dose 1 is strictly above 0 and the linear impact of the complete series is strictly below 0. Having a positive linear impact is somewhat counterintuitive. So we looked into this and found that this may be due to 3 reasons: data insufficiency, delay in the manifest of the effect of vaccination, and COVID-19 virus mutation. After this, we performed F-tests as hypothesis tests for question 1 and 2. As we can see from the left side, the p-values of both hypotheses are much less than the alpha value of 0.05. The test statistics obtained for both hypotheses are much greater than the critical values. These findings lead us to reject the null hypotheses. From the first research question, we conclude that complete series has significant impact on infected cases, given death cases and first dose. From the second research question, we conclude that complete series do not have the same impact on infected cases as the first dose given death cases. Taken together these two, we came to the conclusion that a full series of COVID-19 vaccines can restrict the infection rate, which may indirectly prove that a full series vaccination is able to increase the immunity to COVID-19. Lastly, we used k-fold cross-validation to test the predictive power of the model. The root mean squared error we obtained is 0.0272. The low RMSE suggests the model behaves stably across different data and has good predictive power.
The fourth research question is, does the complete vaccine series have the same impact as the booster shot with the first dose and death cases in the model? The variables are defined as the following. X2 is the number of first dose, X3 is the number of complete series, X4 is the number of boosters, and X5 is the number of death cases, and Y is the number of infection cases. The null hypothesis is beta 3 equals beta 4. The reduced model has X3 and X4 as a combined predictor that has the same coefficient. The alternative hypothesis is beta 3 and beta 4 are not equal. The full model is built under the alternative hypothesis. Here is the model summary of this original model. Before we make any conclusions, we need to check the assumptions underlying multiple linear regression first. First, a BP test is performed to check if the error variance is constant. From the test result, we can see that the p-value is much smaller than 0.05, which means the problem of non-constant variance exists. Then, a Shapiro test is performed. The test also has a p-value much smaller than 0.05. A QQ plot is used to verify the result of the Shapiro test. We can see that the QQ plot of residuals deviates away from a straight line in both tails. So we can conclude that the errors are not normally distributed. To check if there is any outliers, the student heights residuals are compared to 2. It turns out that there are 6 outliers. Therefore, the full model has multiple assumption violations and cannot be used directly. After removing the outliers, a transformation on X is performed. The new predictors are defined to be log of the original predictors. A Baoxuan procedure is performed, and the result shows that Y should be transformed as Y to the power of 0.1. Based on these transformations, BP tests and Shapiro tests are performed again to check the new model. The results of both tests show p-values larger than 0.05, so the problems of non-constant variance and non-normal error distribution are largely reduced. The QQ plot of the residuals is plotted again. This time, the plot better follows a straight line, which verifies the result of Shapiro test, and we can conclude that the residuals are normally distributed. Some more advanced diagnostic techniques are used to validate the model. Added variable plot is performed, and from the graph we can see that each predictor has a marginal effect when added to the model last. We can also see that the marginal effect of the complete series, which is X3, shows a large negative impact on the number of infection cases, and the marginal effect of the booster, which is X4, shows a much smaller negative impact on the number of infection cases. Then, DF betas and DF fits and Cook's distance are used to check influential points. The result shows 0 and 1 influential points in the first two tests, and 0 major and 0 minor influential points in the Cook's distance criterion. Therefore, there is no influential points in the model. Next, we want to check multicollinearity. A plot of each pair of the predictors is shown, and there is no obvious multicollinearity issue from the plot. The VIF values are calculated when correlating one predictor to the rest of them. None of the VIF values is larger than 10. However, we do have the VIF for the first dose to be close to 10. Therefore, ridge regression is performed to remove the impact of multicollinearity. In the first image in the graph below, we can see that k equals 0.12 gives a good regression model. Then from the summary of the ridge model, we can compute a skewed confidence interval for beta 3 as minus 0.68 to minus 0.01, and a confidence interval for beta 4 as minus 0.36 to 0.37. We can see that the complete series have a negative impact on the infection cases, while the booster has almost no impact on infections. We can conclude from the ridge regression that the complete series and the booster shot does not have the same impact. An F-test is also performed on the transformed full model and the reduced model. The test statistic is calculated as 24.15, and the critical value is 3.98. We can conclude that the complete series does not have the same impact as the booster shot from the F-test. Lastly, k-fold cross-validation is performed, and we can see that the RMSE is calculated to be 0.13, which means the error of making predictions with the transformed model is very small. So the transformed model is reliable in terms of making predictions.
The question 5 is, does the number of vaccines have the same impact on the number of death cases before and after the mask mandate was lifted in Indiana? So the x1 is the number of vaccines, and x2, which is a qualitative parameter, is mask mandate. When x2 is equal to 0, the mask mandate is lifted. The null hypothesis for this model is beta 3 equal to 0, and the alternative hypothesis is beta 3 not equal to 0. According to BP test and Shapiro-Wilk test, the original data violates constant variance and normality assumptions. To solve these problems, I did log transformation on X and Baoxuan transformation on Y. After transformation, there is an improvement according to two tests and the normal QQ plot on the right. Building a OLS model with new database, I find that the test statistic FS is equal to 0.1793 and the p-value is 0.6728, which means the interaction factor beta 3 is not significant. Then I continue doing advanced diagonal. As the added variable plot showed, both x1 and the interaction factor between x1 and x2 don't provide much additional information to the model. Then I use H matrix and standardized delayed residual to check x and y outliers. The result showed there is no y outliers but 13 x outliers. However, I used the influence plot to check outliers again. The plot doesn't show any obvious outliers but several influential points. Then I use Cook distance, defeats, and df betas to recheck the influential points. The results show that there is actually no influential data point. And since I include interaction fact in this model, there must be an issue of multicollinearity after testing VIF. To improve the multicollinearity, I choose to use ridge regression with k equal to 0.06, and the result is very surprised as we can see that the parameter x1, the total number of vaccines, actually doesn't play any significant role in the model. To confirm what I got, I used bootstrapping to calculate 95% confidence interval for 3 parameters, and the confidence interval for x1 includes 0, which means it is insignificant, and other 2 parameters have a negative effect on the number of death cases. So the last step is k-fold validation, and I got RMSE equal to 0.0563, which means that my model can make a very good prediction. So the conclusion of this research question is, first, the number of death cases were lower before the mask mandate was lifted, which made our expectation. And the second one is the total number of vaccines isn't that significant when it's in the same model with the qualitative parameter mask mandate.
In conclusion, our project applies a linear regression to explore how number of administered first, second, and booster shots of vaccine and mask influence infection cases and death cases together. According to 2 previous observations, high COVID-19 vaccine effectiveness has been proved, and very max reduced transmission of infected respiratory particles. Therefore, we expected every single shot of vaccine can reduce the infection rate in Indiana, and expected the removal of mask mandate policy increased infection and death rate, even though people have already received the vaccine. Although our models have very strong predictive power, not all of our expectations are reached.
In conclusion, our project have 3 pros and 3 cons. The first pros is the database of our project is very up-to-date since the pandemic just happened in the last 3 years. And the second one is our project can still be meaningful because the pandemic is not completely over. And the last one is we learn how to deal with real-world data, which is definitely much more problematic than the databases we use in the homework. And about cons, the first one is the scale of our research questions can't be completely handled by the relative small database. And the second one is not all our violations of data, such as non-constant variance, were completely solved in our model. And the last one is we didn't plan our project very well, so we didn't set aside more time for the emergency. For the last cons is just about personal issue, and for the second one, we can do some research about advanced treatment to solve the violation of assumption. So the biggest problem now is the first one. So to solve the first problem, we can just scale our current database up. We can scale it up in two directions. First, we can expand our research from Indiana, from one state to the United States to the whole country, to remove the original limitations, and we can also extend the time of data from several weeks to years to give our vaccines plenty of time to take effect, so that we can solve the problem we met in the question 1 and question 2. Our presentation is over. Thank you very much for watching.